The work energy theorem states that the net work done on a system will change the overall energy that the system has. It could increase the kinetic energy of the system, or it could manifest itself in other ways too. Here we see the initial mechanical energy of a system. Now, if this system was isolated, then that initial mechanical energy would equal the final mechanical energy. But here there's a WNC term, and if work gets done from outside the system, that can either increase or decrease the overall energy that the system possesses. So, what type of work is considered non-conservative? Conservative work involves gravitational forces and elastic forces where the energy could be stored for some later use. Like, for example, if you take a spring and you push a ball into the spring, then you're storing energy in the spring. But that energy can later be used to propel the ball forward. So it's conservative. But when it comes to things such as friction and air drag, for example, if you walk across the ground and the ground is rough, then the energy that you lose through your feet, that can't be gotten back. We'll try a bunch of examples here to hopefully make it clear how the work energy theorem works. This one says a rock of mass 0.2 kilograms is going to be dropped from a 5-meter tall bridge. Find the final kinetic energy of the rock and the final speed of the rock just before impact. So here, this involves just gravity. You're going to release the rock and you're not going to have an influence on it after that. So this is going to be a case where the non-conservative work is actually zero. Gravitational forces are conservative. So let's first of all use some formulas that would let us calculate some numbers here. So they tell you how high the bridge is, and they tell you the mass of the rock. So there's actually a formula for gravitational potential energy, and the formula is this: UG equals mgh, where m represents the mass of the object, h represents the height above ground, or wherever you're calling the zero, and then g represents the gravitational field strength. So that's actually what we want to use to calculate this. We want mgh. Alright, so it's going to be, let's see, 0.2 kilograms. G will be 9.8. And then for H, we just want the height above ground, 5 meters. Okay, multiply those, and you get the initial gravitational potential energy of the rock. It's 9.8 joules. How much kinetic energy does the rock have? Well, it's being released, and it's going to fall down. So it has none. It's not moving at the start. It's at rest. All right. How much gravitational potential energy will it have at the end? Well, if you use mgh, 0.2, 9.8, and the h is the height above ground here, so that's 0. So it has 0 gravitational potential energy when it's on the ground. That allows us to find the final kinetic energy. So you see the left side of the equation has to equal the right side. You can solve for it if you need to, but you'll see it's going to all boil down to 9.8 equals kF. The zeros just go away. So this must also be 9.8 joules. Okay, now that we know how much kinetic energy it's going to have at the bottom, 9.8 joules, we want to solve for the final answer, which is how fast is it going. There we would use the kinetic energy formula, 1/2 mv squared. But this time, we know how much energy there is, so we want to plug that in. And then we want to plug in the mass of 0.2. And we leave the v as a variable. And now we just try to solve it. It's 9.9 meters per second.